On December 17, 1903, the history of aviation was changed forever when the Wright brothers made the world's first successful flight. You might think that their design was so simple. The propellers move the aircraft forward, the wings produce the lift, and the aircraft stays in the air. But when you examine it closely, you will be amazed by the numerous ingenious technologies these high school dropouts developed 100 years ago. Their design was so complete that even the current modern aircraft use the same principles of flight. First things first, to make an aircraft fly, you have to first overcome the pull of gravity, or, in other words, you have to produce a lift force. The Wright brothers borrowed the idea of lift generation from their own earlier experience on gliders. They knew that when air flowed over a curved surface, it generated a lift force. The higher the speed, the more would be the lift force. An increase in angle of attack also increased the lift force. How is this lift generated? That's a topic for another video. To make the aircraft move forward, two propeller blades were used. They produced thrust force, again from the same airfoil principle. The thin propeller blades were a clever design choice. Until then, the common belief was that an aircraft propeller should be something like that of a ship's propeller. However, the Wright brothers proved that to work efficiently in air, a high-speed, narrow blade was the ideal choice. Moreover, you will notice that the blades were rotating in opposite directions. This was another crucial design decision. Without this, control of the aircraft would not have been possible. We will learn about that at the end of the video. The blades were driven by an engine which sat on the wing. To fly an aircraft, you have to obey the following force equations of flight. To come up with an aircraft design which satisfied these equations, the Wright brothers developed their own lift data by abandoning all the wrong lift data that was available at that time. The Wright brothers' wing had the top point near the leading edge. This design produced much more lift than the top at center design used at that time. With an optimized wing design alone, this aircraft would not lift from the ground. The Wright brothers realized that the existing heavy automobile engines being used were the main villains. They had to make the engine lighter without compromising its power output. Only a powerful engine could give the aircraft a good speed. As explained earlier, the more the speed, the more the lift. Unable to find any such engine, with the help of their mechanic, the Wright brothers designed and built their own engine, a lightweight 12-horsepower petrol engine. Even before the new engine development, the Wright brothers had calculated that they needed an engine of less than 200 pounds in weight, with at least 8 horsepower to meet the equations of flight. To reduce weight, they even cast the crankcase with aluminum, a first at that time. They painted the crankcase black so that their competitors would not know about the construction material. You can see the details of the chain and sprocket mechanism used to transfer power from the engine to the propeller blades. With this design, at proper airplane speed, the lift force would overtake the gravitational pull and they would have takeoff. Did you notice a rail track in this visual? That was another clever design decision from the Wright brothers. They knew that it was impossible to get a good airplane speed in the sandy terrain, so they used a 60-foot-long rail track arrangement for a smooth takeoff. The Wright brothers' main innovation was the development of successful flight controls. Aircraft crashes were a common issue in those days, and nobody knew how to control them. To have a successfully controlled flight, the Wrights had to control their plane in 3 axes: pitch, roll, and yaw. They again relied on the principles of the airfoil to accomplish this task. To pitch the airplane, the Wright flyer had an elevator arrangement at the front. You can see that by moving this lever, a rope mechanism changed the angle of the elevator. If the elevators rotated up, there would be an upward lift force as per the airfoil principle. The torque produced by this lift force could push the whole aircraft up as shown. To push the aircraft nose down, they just did the reverse. In modern airplanes, the elevators are fitted at the back. To roll the aircraft, Wilbur Wright had a great idea: wing warping. It was clear that by twisting the wing along its length at one end, the angle of attack would be positive and the other end it would be negative. This would obviously create a lift differential and the airplane would roll. To understand how the Wright brothers practically achieved the wing warping, let's have a look at this animation. The pilot controls a cradle using his hip, which in turn controls two separate cables attached to it. The cable movement makes the wing warp through a clever mechanism. This is a brilliant mechanism. We need a separate dedicated video to understand the details of it. In modern aircraft, ailerons are used to generate the lift differential. However, when the Wright brothers first tried to roll the aircraft using wing warping, the result was disastrous. They noticed that along with the rolling, the airplane took an unintended turn as shown. They called it a steering reversal problem. This phenomenon is now called adverse yaw. The physics behind the adverse yaw are now well understood. The airflow above the high-angle wing region produces high drag. On the other tip, the drag force is low. The difference in the drag force makes the airplane yaw as shown. The Wright brothers overcame this issue with the help of a rudder arrangement. If the aircraft was yawing in this way, they turned the rudder as shown, in such a way that the torque produced by the rudder would exactly cancel the adverse yaw torque. Here, the Wright brothers made another smart move. Since the rudder had to be operated whenever there was wing warping, they connected the rudder and wing warping controls together. Both these motions were simultaneously operated from the hip control. By using these controls effectively, the Wright brothers were able to give the aircraft the stability needed, pitch the aircraft to climb up or climb down, and make a smooth turn by banking the aircraft. Now, back to the interesting question posed in the middle of the video. Why did the Wright brothers use opposite direction of rotation for the blades? This was to cancel the gyroscope effect of a rotating wheel. Any rotating object has an angular momentum. Assume the Wright brothers designed the aircraft with the blades spinning in the same direction. Now the pilot decides to pitch the aircraft by lowering the elevator. The lowering of the elevators would obviously produce a torque as shown. However, the airplane would not pitch upwards as expected due to the angular momentum of the blades. Instead, it would take an unexpected side turn as shown. This unexpected phenomenon is known as gyroscopic precession. Gyroscopic precession conforms perfectly with Newton's second law of motion. You can see that the direction of change in angular momentum is the same as that of the torque applied. The only way to overcome such unexpected behavior is by eliminating the very cause of it, the angular momentum of the spinning blades. That is exactly what the Wright brothers did with two blades spinning in opposite directions. It is astonishing to discover that the Wright brothers thought about such detailed engineering points despite their limited formal education. Did you notice that the pilot's position was not in the middle of the aircraft? Please support us by clicking the Help button if you are astonished by the marvelous engineering feats that the Wright brothers accomplished. Also, let us know in the comments box why you think the Wright brothers decided to position the pilot slightly off-center. Thank you.